So we left off, we were talking about qualitative or categorical data and organizing it in the frequency table and our two different graphs, our bar graph and circle graph. So now let's look at the quantitative data, or numerical data. Remember, there's two types of quantitative data. We have discrete and we have continuous, and they're treated differently. Discrete data, and in fact, discrete data can sometimes be treated in two different ways as well, but we're going to talk about limited discrete data. By limited, I mean there's a small number of possible values it can take on. For example, let's say we survey people to ask how many classes they're currently taking this semester. Well, your answers, you wouldn't answer 0 because then you wouldn't be a student and you wouldn't be part of our population, correct? So your answers would be 1, 2, 3, 4, and let's say nobody is taking more than 5 that we sample. So then we'd do our tally and our frequency. Now, this would be done the same way we did with our colors. You'd have this list of 1s, 2s, 3s, 4s, 5s, or whatever. We'd tally them up and write the frequency in. We're going to go ahead and just fill in the frequency here. So we have 19 students that are taking 1 class, 28 that are taking 2. We have 51 that are taking 3 classes. Say we have 72 that are taking 4 classes right now, and 30 that are taking 5 classes at a time. So there is our frequency table. Now, we could, just like we did with our categorical data or qualitative data, we could do a relative frequency. Relative frequency would be done the same way. So I'm going to pause this for a second here and see if you guys can figure out how to fill in the relative frequency. So in your notes, fill in the relative frequency for this table of data. So our first step is to find the total. What did we get for a total? 200. So each of these is divided by 200 to get the relative frequency. 19 divided by 200 is 0.095. Yep. 28 divided by 200, 0.14. 51 divided by 200, 0.255. 72 divided by 200, 0.36. And 30 divided by 200, 0.15. Those are relative frequencies. They better add up to 1.000. We're really close to it. In this case, we didn't round any of them off, so it better be exactly 1.000. With quantitative data, with numerical data, there's a third type of frequency we can worry about. It's called cumulative frequency. What cumulative frequency deals with is that value or less. Sounds complicated, but it's not so bad. 1 has a frequency of 19, so the first value is going to be the same in our cumulative frequency. 2 has a value of 19, but it's that value or less. So 28, plus the 19 that were for the 1. So that's going to be 47 is the cumulative frequency for the 2. Because there's 47 that are either 2 or less. So either 2 or 1 in this case. For 3, we've got 51 plus the 28 and the 19 that are smaller than it. I'm going to take it easy and do 51 plus 47 is 98. So that's the cumulative frequency. There are 98 values that are equal to 3 or smaller. For the 4, there's 72 plus the others that are smaller. That's now 170. 5 has 30 plus the ones that are smaller. It's 200. Notice this cumulative frequency for the last value better be the same as the total frequency. We're not going to get into it in this course as to why this is an important thing, but there are a lot of applications and probability and stuff like that with our statistics where this is an important value. In fact, if we have a little time tonight, we may talk about grouped means and medians, and that's an important value for doing that. From this, we can create the same types of graphs we did for our categorical or qualitative data, except a bar graph is not called a bar graph when it's for numerical data. It's called a histogram. The big difference between a histogram and a bar graph is now, of course, it's numbers across the bottom here instead of categories. Colors is what it was before. We're still going to be labeled up the side here. Our largest number was what? 72. So this one's labeled by tens. There's going to be another difference that comes up here. We had 19 with one class and 28 with two. Three classes was 51 and 72 for 4. And 5 was 30. Looking at this graph, it would not be easy to tell which is larger, 2 or 5, because they're very close in values. Like I said before, graphs are not good for finding exact values. It's pretty easy here to see that 4 is the most common number and that 1 is definitely the least common number. But again, I couldn't give you an exact value on any of those unless I went back to the table. Now another difference you'll see here between the histogram and the bar graph is the bars on our histogram are touching each other, and on the bar graph they weren't. There is a mathematical, psychological reason for that. In statistics, we actually do involve a little bit of psychology and cognitive function and how we represent data. Up here, when we're graphing colors, there is no link between red and blue and green. In fact, there's no even logical order. I could put them in whatever order I want to, and it doesn't affect anything. Well, down here with the numbers, not only is there a logical order, numerical order, 1, 2, 3, 4, 5, but 1 flows into 2, 2 flows into 3, 3 flows into... They border each other. So we have the bars touching each other to represent that. There is a connection from one to the next. We have that space between the bars for the categorical data because there is no connection from one to the next. Yeah, very subtle point, but we're talking about representing data accurately. It's part of the honest representation of data. We can do bar graphs, we could do, or histograms, we could do circle graphs if we wanted to. Circle graphs are generally, though, for the categorical data. So that was discrete and limited discrete. Obviously, if we were counting how many hairs are on your head, we wouldn't be able to list out every possible number there. We'd have to group them. And that's the next thing we're going to be looked at is grouped numerical data. So group numerical quantitative data. For example, the hairs on your head example is a little outrageous, but if I wanted to do what is your GPA? Well, if we're calculating the GPA down to the nearest to the 100th of a point. So obviously we go from 0 up to 4.00, but that's 0.01, 0.02. There's a lot of different values in there. We cannot possibly list out each of those values separately. So we're going to group them. Those groups are sometimes called classes. And there are two rules about those groups. One is it must cover all possibilities. In other words, there can be no gaps. And two, they must all be the same size. Now for GPA, there's some pretty common sense groups I'm going to use. We go from 0.01 to 1, 1.01 to 2, 2.01 to 3, 3.01 to 4. The lowest now there is one little gap here. It is possible to have a 0.00 GPA. In other words, you failed everything. Well, we're going to claim that what we're going to do is we're going to define our population here to be students who have successfully completed at least one class. So if you have completed and passed at least one out of 100 classes, you're going to have more than a 0.0 GPA. So that's how we're going to get around that. So it's not possible. If you're 0.00, you're not in this population. We said that it was measured to the nearest 100th of a grade point. That's why I had to go 0.01 instead of just 0.1. If I had said we're only going to the nearest 10th of a grade point, then a 0.1 to 1 and 1.1 to 2 would have been adequate. But when I say to the nearest 100th, well, I've got to have it like that. Otherwise, you can fit in between. We don't want you to fit in between classes, in between groups. And it does cover everything. So I'm just going to list this as GPA. I might say GPA classes. So one of the GPA groups. And frequency. Again, I would have all the GPAs in a list, and I would go one by one and put them in each group that they were in. To save time right now, we're just going to make up some frequencies here. Hopefully there's not too many in that 0 to 1. We're going to say there's 12, 38 in the 1.01 to 2. This is a little more reasonable. Let's say that there are 61 in the 2.01 to 3 and 39 in the 3.01 to 4. So we've got our GPA classes. We could, once again, do relative frequency and cumulative frequency. But at this point, for the sake of time, I'm going to trust that you guys understand that. If you don't, let me know and I'll go through it with you later. But we could fill those in just like we would with other numerical data. Remember, the cumulative frequency is only done with numerical, not quantitative. And these could be graphed in a histogram just like our discrete data. Slight difference would be, instead of single numbers along the bottom, it's going to be these ranges. And again, our bars would be tight together. I just slapped those in. I didn't put a scale or anything, obviously, so don't hold me to those being accurate. You guys get the picture. I know I'm kind of getting sloppy here, but for the sake of time, I'm kind of moving along. So we're going to represent those graphically. There is another type of graph that fits a different type of data. What we have looked at here is what we call, it's basically snapshot data. It is data that's taken at a single point in time, and we're getting a picture of that data. There's another type of data called time series data. In time series data, we're only looking at one thing. Here, the previous stuff we looked at a single point in time and we broke up all the stuff into different possible categories. For time series data, we're only focusing on one thing, but we're looking at it at different points in time. We might look at tuition cost. Cost per credit. We'll go year 2000, 2005, bless you, 2010, and 2015. Let's see, in 2000, it was $98 a credit. 2005, it was 109. No. 2010, let's say it went up to 141. 2015, it dropped to 138. They're not too far off, but no, they're not. There was a year in there where it dropped, but I can't remember, it was like 2013 or 2012, it actually did drop a couple bucks a credit. So we're going to put our dates across the bottom. Time always goes across the bottom of our graph for these. And our value goes up the side here. Now I'm going to do something bad. I'm going to do that. So this is going to be 90, 100, 110, 120, 130, 140, 150. I'll explain why what I did there is bad in just a minute. So in 2000, it was $98, right about here. 2005, 109, right about there. 2010, 141, jumped up to here. In 2015, it dropped just slightly. So we're going to draw lines connecting those points. Now, a lot of people are really tempted to draw a line from the origin up to there. It was never $0 for tuition. So that would not be an accurate point. So resist that urge to connect it back to the beginning down there. This is called a line graph. And its power is in the slope of the line. We can see where it's increasing the fastest, right here, because the line is the steepest. We can see where it's decreasing. There's only one spot, that's here, because it's sloping down instead of up. Again, if we wanted to find exact values, looking at this, can I tell that that's exactly $98? No. I can tell it's right around 100, maybe a little bit less. If I want the exact price, I've got to go to the table. Okay, so I said something about this little thing here being bad. One of the things in statistics is that statistics gets used a lot in an attempt to deceive. That's one of the things that can be used to deceive. If I am a company and I'm trying to prove to you that my company is better than my competition, so I'm going to have me, and then competitor A and competitor B. I'm going to make this graph that shows sales. This is A, this is me, this is competitor B. Looks like I did really well, doesn't it? This is going to be in thousands of dollars. probably label it like this to make it a little less obvious. Looking at this, it looks like I sold 2 or 3 times as many as A and 3 or 4 times as many as B, doesn't it? But if I look at the numbers, it looks like B sold about 191,000, A a little over 190,000, and I sold between 194 and 195,000. Not that much more, is it? But the way the graph is set up, it looks significant because of that. I didn't start at 0. I started at 190,000 and I numbered up from there. Now this has its advantages. It's easier for me to see the difference between the numbers. But also if I'm trying to present this to a consumer, their eyes are drawn to the fact that my bar is 2 or 3 times as large as the other ones. In reality, this bar graph looks something like this. Yeah, mine's taller than theirs, but not much, right? This comparison is much more precise. It's saying, hey, we're pretty close, but I am better than them. Not 3 times better than them. As we go through statistics,